Catherine. The next presenter that we've got coming up, who will be speaking to us about data, information, and knowledge, and what information we need to inform environmental markets and green investment streams, is Dr. Anna Richards from the CSIRO. So, Anna can get the slides up. Anna is a senior research scientist and leader of the Ecosystem Dynamics team at the CSIRO Tropical Ecosystems Research Centre in Darwin, in the Northern Territory. Of course, she has worked in environmental economic accounting for more than 5 years, where she applies frameworks for evaluating natural resource management activities based on an understanding of dynamic ecosystem condition set within a state and transition modelling context. She's recently started work in nature markets with a focus on forecasting ecosystem condition. So thanks so much, Anna. Looking forward to, unpacking some of those ideas.
Thanks, Rachel. Can you see my screen okay?
We can see it perfectly. Thank you.
Great, I'll get started. I realise I put 13th of May, so I'm a day behind, but anyway, see how we go. Okay, I'd like to begin, and thank you for having me. I'd like to begin by acknowledging the Larrakia people as the traditional owners of the land where I'm working on today, and pay my respects to their elders, past and present. I put up this quote because I wanted to distinguish between data, which is sort of information we have about specific instances, and knowledge, which identifies information about general concepts. So I think both data and knowledge will be critical for nature repair markets and environmental investment. And I've sort of arranged this presentation around those 2 points into 2 parts here. So starting with data, we have lots of data, I guess, that's useful for markets, and particularly for understanding the current environment in which you might start to prioritise investments and actions. And data is really coherent information that we have about past to present. So it's observations and measurements that can be organised in a way that is consistent and comparable across different space and time, and across different places. It's important to have frameworks, and I've put one up here, the UN System for Environmental Economic Accounting, Ecosystem Accounting Guidelines, for reporting this information in a way that's coherent and consistent. And I'll give an example of how accounts can be used as a baseline for prioritising actions around nature markets and environmental investment. And the system of environmental accounts provides information in a sequence, and you can see that diagram on the right there, around the extent, conditions, services, and biodiversity associated with our ecosystems. And this consistent and standardised way of reporting is useful for scaling projects, and also for quantifying values of our different ecosystems. So one of the critical pieces of information is that of the current status of ecosystems, and we usually use a term called ecosystem condition, or condition of natural capital, to describe this. So ecosystem condition is the quality of an ecosystem measured in terms of its abiotic and biotic characteristics. It's assessed in terms of the degree of retention or loss of reference condition attributes. And that reference condition, when we're referring to the definition under the System for Environmental Economic Accounting, is a level against which past, present, and future ecosystem condition can be compared and measured relative to relative change over time. And it reflects high ecological integrity and the capacity to continue providing habitat to support biodiversity. And so that term natural capital is interlinked with this idea of ecosystem condition. And natural capital is the stock of natural assets within an ecosystem. And you can think about this as the characteristics of that ecosystem, its structure, function, and composition, which combined or integrated gives us an understanding of ecological integrity in that ecosystem. And consistent and comparable condition metrics can be used to track ecosystems over time. So I'll give you an example of some a condition index that we've calculated recently from a set of regional ecosystem accounts for the Flinders, Norman and Gilbert River catchments in North Queensland. This shows 2 ecosystem types from quite a number that were assessed in this catchment. And they both showed a decline over 30 years, over 18 years, in ecosystem condition, which was a result of a change in extent of different ecosystem states in these 2 ecosystems, and I'll talk about that in a few slides on. You can see both ecosystem types have some variability in that declining trend over time, and condition was higher in the in the inland floodplain eucalypt forests and woodlands compared to the tussock grasslands. The condition of ecosystem types in the previous example was determined using the Habitat Condition Assessment System, or HCAS. And this is a general framework for monitoring habitat condition across entire regions or the continent using satellite remote sensing and site reference data. And this reports on the capacity of habitats to support regional biodiversity persistence. Reference ecosystems are representative locations where ecosystems have high integrity. And these reference ecosystem locations are often inferred or provided by experts in different regions across Australia. These are combined with environmental covariates and remote sensing data to model and predict reference patterns of ecosystems and simulate the variety of Australian ecosystems based on their remote sensing characteristics. Then there's a condition benchmarking algorithm that uses predicted and observed remote sensing characteristics and representative reference sites to determine the departure of reference of any pixel in Australia from high integrity reference sites, and that gives us that condition layer. From the ecosystem condition data, it's possible to derive biodiversity persistence in a particular location. But this includes additional information on landscape connectivity of ecosystems in different condition states. So once that ecosystem condition layer is combined with those landscape metrics, then we can report biodiversity patterns. We can compile them into account tables, and there's an example here, and these can be reported at different levels, so at levels of biological groups like birds or reptiles or plants, or for individual species, or for groups of species like threatened species. Here's an example of some of the patterns that were observed for the Flinders, Norman and Gilbert River catchments. And this is biodiversity persistence of plants, reptiles, birds and threatened species across that 18-year time period. And you can see there's some variability. This region has quite high biodiversity values relative to other places in Australia. You can also see the numbers down the bottom, which is just a change in those numbers of species persisting across 1 year, which we don't expect much change in a single reporting year. But in an account table, there's usually an opening and a closing account across a single 1 year time period. So we spoke about data that provides a baseline for understanding our current extent, condition and biodiversity, and the system of ecosystem accounts, which provide standards and frameworks for reporting on that. Now we want to move to knowledge, which we need to understand how management interventions can link to future biodiversity gain. So given this is in the realm of forecasting change, we need to draw on expert knowledge and modelled information. So some information has been collected from existing trials. So regional land partnerships, long-term monitoring projects are a good example of where we're collecting information to understand the effectiveness of different management actions. But you can imagine there's much of this information maybe observational expert knowledge that's not been recorded in reports or scientific literature and other places. So what we need in order to make use of this knowledge is a coherent conceptual narrative of change to produce that knowledge into a shape that's useful for decision making. And one tool we've been using to generate information about the effectiveness of different management actions for enhancing or protecting biodiversity are state and transition models. And these models can be described in a standardized way across the country to capture and express nonlinear change in ecosystems. They can be easily communicated, relatively easily, in the box and arrows there. They explicitly include human actions, and they can be populated with many different types of data and information, including expert knowledge. And there's two simple parts to these models. One is description of ecosystem states, or you can call them ecosystem condition states, and they can be in a reference or in modified condition. So ecosystem states group common types of modification that we observe in our ecosystems relative to a reference. And so they have to have unique combinations of structure, function, and compositional characteristics. And they're often resilient to disturbances or perturbations. And then that's an example of an ecosystem state there. And then the other part of the model are transitions, and these are the arrows between the states. And they describe the pathway to which an ecosystem may pass from one state to another. And the important thing is that they're irreversible without active management intervention or a very long time frame. And you can describe these transitions by their driver, their time frame, how long it will take, and the likelihood that given those drivers and that time frame that transition would occur. And these probabilities are often derived through expert elicitation and are really critical for understanding the future likelihood of a management action being effective in producing a change in biodiversity. So I'll give you an example of how we've pulled some of these pieces of data and knowledge together to generate a possible workflow for forecasting future change in landscape condition and therefore future change in biodiversity persistence. So we start on the left-hand side, which is where we've articulated a need for coherent standards and frameworks. So you can integrate information that is already existing at the local and regional scales in a way that's consistent across the nation. And I've given some examples of templates, the Habitat Condition Assessment System, and something called the Australian Ecosystem Models Framework to help with that part. Then we have the next box, which is around regional expertise and information, and this is where all that valuable and wonderful expert knowledge comes in. This is where ecosystem state and transition models are described, and that includes the current ecosystem states we see in landscapes and the types of management actions that might shift you from one state to another in the future. And also includes some regional information on the location of reference sites that can enhance the Habitat Condition Assessment System prediction of that condition layer, that starting condition layer for your region, and therefore the starting baseline level of biodiversity. And the next step is to apply different restoration scenarios. So given sets of management actions, which one would you apply in a landscape? And then as a tool for predicting then that future landscape ecosystem extent or extent of ecosystem states and their associated condition. That gives you a habitat condition layer in the future. And then you include those metrics on connectivity and distributional shifts in species composition due to climate change to get the future biodiversity persistence. Or if you think about another way, the expected benefit of a proposed action on landscape scale species persistence in a region. And then there's some feedbacks, of course, because then these actions would get applied in a landscape and we'd have some learning about the effectiveness of different actions that we may not have known very much about at the start. And that can feed back into these models or state and transition models or your likelihood of transition. And the local monitoring data can also, of course, inform or validate some of the biodiversity persistence models as well. And Catherine mentioned this in her talk. So some of this workflow that I've shown in the previous slide has been piloted in something called the Ecological Knowledge System for the Nature Repair Market, which is led by Helen Murphy and is a collaboration with DQ and ANU. And it consists of 3 activities. The first one is First Nations Knowledge and Values Framework, which is an Indigenous-led and co-designed framework for how First Nations knowledge and values would be incorporated into an ecological knowledge system. The second part is a regional toolkit, which is linked very closely to what I showed in the previous slide, which is generating or generating a method for expert elicitation of state and transition models. And the third part is the desktop biodiversity assessment method, which is taking the state and transition information, including the effectiveness of management actions, and then using that to calculate expected benefit for biodiversity and delivering that through the planner platform that Catherine showed previously. So some of those outputs include a population of the regional toolkit for North Central CMA Victoria, and I see Matt's on the both Matts are on the line. The other region is the Burnett Mary Regional Group in Queensland. So we've just been lucky enough to spend some time with both these regions over the last 2 weeks, running some state and transition modelling workshops, talking to experts, bringing in all the wonderful data and information that's been gathered in these regions for many years, and seeing how they can be used to inform future biodiversity persistence in the landscapes. And then these methods, typologies, templates, and the pilot then combine into a nationwide implementation plan. And that's it. Thank you.